Chapter 10 is all about solutions. Before we can know more about the solutions, we need to actually define what the solution is. A solution is defined as a homogeneous mixture of two or more substances in one single phase. When we say the homogeneous mixtures, what does this mean? Okay, these need to be homogeneous at the molecular or atomic level. Before we can actually elaborate this a little bit more, let me actually just introduce the important components that we need to know. A solution has two components, okay? One is called solute. The other one is called solvent. So the solute is the less abundant species, and the solvent is the more abundant species inside the solution. When you have solute plus your solvent and form a homogeneous mixtures, you got your solution. And then we always say the solute is dissolved in the solvent. So that's how we define the solutions. Okay, so the very simple definition, okay, basically is you have your solute, you have your solvent, you blend together, they form a homogeneous mixtures at the molecular or atomic level. We call it as a solution. So example of solutions. Hope this will give you a better idea. Salt water is actually a solution. Inside here, we know the solvent will be your water or H2O, and the solute will simply be just your salt. To give you more chemistry flavors, it will be just sodium chloride. One thing you want to be careful is actually if you throw in your sodium chloride, which is actually the white solid, if you put it into the waters, the white solid disappear, right? Because the sodium chlorides, when they dissolve inside water, they become sodium plus and chloride minus, and those things actually surrounded by the water molecules. Then they form a homogeneous solutions. So we call this is actually a liquid phase solution. Another thing is actually the sugar water. Okay, sugar water. Okay, sugar have this very unique chemical formula. It also look like a white solid powders when you throw it in. You also dissolve inside the solvent, which is your water. And then after a while, it becomes also transparent. So once they dissolve inside water, this one did not do the things like sodium chloride. It just exists as the sugar form, but it forms hydrogen bonds with your water so that you actually stay late molecular forms inside water. So it also forms a very stable solutions. But solutions doesn't necessarily to be in the liquid phase. It can also be in the gas phase or the solid phase. Air is actually one of the most commonly seen solutions in the gas phase. Inside our air, we have around 20% of O2. So O2 is our solute. So inside our air, 80% are nitrogens. So these are the actually example of the solid solutions. So brass is actually one of the metals that you see a lot. The majority of brass is actually coming from copper. That's why you see these shiny gold colors on the brass. But inside there, there's actually certain percentage is actually coming from the zinc. Okay, and they form a homogeneous solution. Ruby is also a solution. So majority is actually just aluminum oxide. But with certain solutes, make it become a very valuable jewelry. Okay, I guess that's something that you want to know in the future once you get a ruby from your significant halves. All right, so let's actually some examples of solutions in either liquid, gas, or solid phase. So what are the species that doesn't consider as solutions? So these are the two examples. The mud waters is not a solution. For the liquid solutions, In the old time, the way people judge it is actually through the how transparent the solution is. But as time goes by, human actually inventing a lot of things, including the nanoparticle solutions or mixtures. Okay, so it also looks transparent. So that definition become less useful. So when you have the mud waters, it actually looks very cloudy. What happens inside is actually your water is still water. Your mud is actually a tiny dust inside your solution. So these little dots represent the little solid materials. Okay, they did not actually interact with your water at all. Therefore, they just suspend inside the solution. Under these situations, we call it heterogeneous solution. Most of the things we talk about in this class was defined as this homogeneous mixture. Okay, not a heterogeneous solution. For chapter 10, all the things that we talk about will be actually fall within this aqueous solution, which means is actually the solvent is always the water. Depending on the type of solute you have, you can either have the electrolyte solution. That means the species, when it goes into your water solutions, it dissociates so that you have both anions and cations coexist inside your water solution. For the non-electrolyte solutions, all you have is actually just the molecule itself. For example, the sugar, once they dissolve inside your water solvent, they actually stay the same form as sugar. So structure-wise, it did not produce any cations or anions inside the water. So electrolyte solution and non-electrolyte solution, the way you make the judgment is whether you have this positive or negative charges coexist inside the solution. The next question people will ask is actually how concentrate the solution is. For the dilute solutions, you have fewer solute molecules compared to the more concentrated solution where you have tons of solute molecules inside your solvent. So what we are going to do today is to introduce you the concept about 5 different definitions of concentrations. So the first concentration we are going to talk about is called the molarity. So the definition of molarity will be number of moles of your solute divided by the volume of your solution. The volume must have the unit of liters. The number of mole of your solute can be calculated through the mass of your solute divided by the molecular weight of your solute. Give you one example. Find the molarity if 5.22 grams of sodium chloride is dissolved in enough water to form 125 solution. So when you read these type of questions, first you need to know what you have, right? 5.22 grams of sodium chloride. From here, you should know that the mass of your solute is going to equals to 5.22 gram. And then the things you want to calculate is actually your molarity, right? That means you need to know number of mole of your solute. And then you also need to know the volume of your solution in liters. So when you read this one, you know eventually you have 125 ml of solutions, right? So that means your V solution is 125 ml or 0.125 liters. And to calculate your number of mole of your solute, then you need to know the molecular weight. And then we know the molecular weight of your sodium chloride is going to equals to 58.44 at the unit gram per mole. Okay, so what you do is actually 5.22 divided by 58.44. So that will give you the number of mole of your solute. From these two, then you can calculate your molarity is equals to number of mole of your solute divided by the volume of your solution. And this will give you a number of 0.715 m. Another thing that you will know is actually calculate this normality. The calculation is actually very simple, okay? It's just your molarity multiply the number of equivalent. Okay, so what is number of equivalents? Typically, this is relevant to these two types of solution. One is so-called the acid-base solution. The other one is oxidation reduction solution. I assume everybody know what acid is, right? So the acid is actually a species. Once it dissolves inside the water, it will produce the protons. Here I use hydrogen chloride as example. So in this case, you can see for this acid solution, one hydrogen chloride produce one protons in the equation. But sometimes we have this acid, for example, the sulfuric acid. Once that dissolve in water, it actually produce 2H plus. So you can see one acid solute produce two protons here. Under this case, we can define the number of equivalent is going to equals to 2 because one sulfuric acid produces two equivalent protons. So using this concept, then you can actually solve this one very easily because we know the normality is just the concentration of molarity, which is 3.75 times the number of equivalent. In this case, the number of equivalent is equals to 2, right? Then you know the answer will be 7.50 N. So let's how you calculate the normality. So another situation is oxidative reactions. So here actually I give you one examples. For the oxidation reduction, if they want you to calculate the number of equivalent, it will give you the equations. This is actually one example. So you can see MnO4 minus, you are going to interact with 5 electrons to produce one manganese 2 plus. That means one of this is going to consume 5 electrons. In this case, your number of equivalents is going to equals to 5. The question here is asking you finding the equivalent mass of this. So first you need to know what is the definition of the equivalent mass. The equivalent mass is going to equals to the mass of the target species divided by the number of equivalents. You have 1 N of these solutions. We assume there's 1 liter. That means you're going to have 1 mole of MnO4 minus. Then you check out the molecular weight of these guys. You can check out the molecular weight of that species from your periodic table so that we can calculate the mass of your MnO4 minus is going to equals to 1 mole times the molecular weight 158 gram per mole, which give you 158 grams. Then you know the equivalent mass will simply equals to the molecular weight of your MnO4 minus divided by the number of equivalent. So that will equals to 158 divided by 5. So that will give you 31.6 grams.